As chair of this session, it is my pleasure to actually introduce the person who started it all. He's the academic father of Michael Weinstein, George Papanicolaou, who's going to speak on coherence and imaging.
Okay, well, thank you. That was quite an introduction. It didn't start with me, it started well before me. But it's a pleasure to be here. Mike and I go back many, many years, at least 35 and counting. So I'm probably the person that is closest to you from the point of view of time. And I have watched with a lot of admiration and pride to say so openly with what he has done, his achievements and his, well, you know his work, the coherence of his work. So anyway, I decided to talk about coherence today. And it's going to be a bit of a, I don't think any of you are really experts on imaging, so I'm going to go slow in the beginning. There is a result in the end, which I think, I hope you think is interesting anyway. But I want to introduce it in a general way so you can see where things are coming. I've been working in this area for a long time now, for more than 15 years. So, and I put here my collaborators over the years. So let me begin with what we're talking about. So the word coherence, it's hard to say in general what coherence really means. So I put down here, describes roughly how effective array imaging is likely to be. In other words, when you go out there, you want to image, you know, you have expectations. Sometimes you would be satisfied with just knowing that there's something there. It's a detection that there's something there instead of nothing, or that you will be satisfied only if something really comes up with very high resolution. And the difference between the two is really a coherence issue, as I will try to explain. I will, you know, in this subject, in trying to present it to you like this, I kind of stylized it, and I will identify 3 ways in which loss of coherence is realized. There are many others, but anyway, 3 general ways. One is in a homogeneous medium at high frequency. So the third one is when the medium is homogeneous. In other words, there's an object out there I want to image. I have an array of sensors here, and I try to form an image by some kind of a reflection process. I send the signal out, I get a return, I record the return, and from the reflections that come back, I try to figure out what it was that I was looking at over there. And if the medium is homogeneous between me and my array and the object, but when I receive back the signals, I only record intensities. I lose the phases. Why does this happen? That happens actually quite often at relatively high frequencies. Anything above, it's a technology that is changing. I used to say with a lot of confidence that you cannot have optically coherent imaging in optics at very high frequencies. But in fact, that has changed, and now that you can even do coherent optical imaging. But in practice, except with very expensive, very high-tech instruments, you cannot record phases in optical imaging. In other words, optical imaging is all intensity-based. You lose phases, or you lose the instruments record at a frequency which is much lower than the frequency of the signals that you try to sample, to record. But the real cutoff is down in the gigahertz regime. Today, in the gigahertz regime, sometimes you have trouble recording. Today, for example, if you want to record directly without so-called downsampling, radar at the 10 gigahertz range, the X-band radar, which is really the bread and butter range for a lot of imaging, synthetic aperture imaging, you cannot do it without tricks that bring the frequency down. It's only very recently, I would say, that with very expensive instruments you can do it. So you can see how the technology is changing and how this importance of having phases or not having phases is changing. And the point that I'm going to make towards the end of, if I get there, towards the end, will be that in fact, not having phases, not recording phases is not the end of the world. You can actually, it's almost as if you have phases, provided you have enough illumination. So really, the problem becomes an illumination issue. How well can you illuminate the object that you want to see? All right, so I'm going to begin with a formulation of the imaging problem. What kind of an inverse problem it is? It is an inverse problem. Then I'm going to say a little bit about imaging with a time reversal matrix, because that's an important thing. You'll see what I mean by that. I will say a little bit more about this loss of coherence, what the modes for the loss of coherence are. And then the idea of how you can really recover phases, unrecorded phases, by having rich enough illuminations. Okay, so this is the plan. Here, now I'm going to put some of this stuff on the board so that we can refer to it. The array is schematically, it's a panel like that. It's where I put sensors here. Okay, so this is XS is the location of the sensor that is firing out. There's an object over here, like that I want to image. I want to find its location and its shape and whatever other features it might have. And I put around it a box. I don't really know where this object is, but I'm going to put a box around it. Okay? And this is called the image window. Okay? So this is the array, XS. So a signal goes out from here. It's a spherical wave. Then it doesn't have to be a spherical wave, but let's assume it is a spherical wave. And then it goes out there. It strikes this object. And then it strikes this object. And then a spherical wave emerges from here. This is usually relatively small compared to the wavelength of the wave that is coming. It doesn't have to be a spherical wave emanating. It could be a bit more complicated. And then eventually this gets back here and it is recorded. So what I record here is a function of time. This is time. So there's nothing for a while until it leaves from here. Let's say a pulse, a sharp pulse leaves from here, goes over there, returns, and then you get a signal and maybe a little bit of a reverberation depending on what this object is. And this is really what is recorded here at XR. Okay, so this is the schematic. And now there are three physical parameters here. One is lambda, the wavelength. Okay, that's the central frequency of this wave. Then there is a bandwidth. I didn't put it in, but there's a bandwidth also. Didn't put it there. That's basically this, the width of this object. There's a carrier above it. Then there is this range L, the distance between here and here. This is the range. And there's the size of the array, A. So these are the three physical parameters, and they translate when I discretize, because it's going to come down to a linear algebra problem. When I discretize this, there will be of the order of n sensors. Here, this will be n sensors. They will be close enough spaced. In order for a collection of sensors to behave like an array, they have to be spaced relatively close to each other, of the order of half a wavelength or so. So the n and the a are related. So n will be the number of sensors. Then there's going to be the discretization. The discretization of the box is the points in the image window. The image window is the area that I want to explore to see if there's something in there. Okay? So I will associate with each point. I come up with an a priori discretization. The choice of the discretization of the image window is something complicated. I have to figure it out how to do it from some understanding of the basic physics of what is the best resolution that I can have in there. For example, a very ambitious choice of discretization for the image window is half the wavelength, because I know that for relatively narrow band signals, I cannot get a resolution in here better than half a wavelength. So I could put a priori a resolution of about a half a wavelength in there for the pixelization, and therefore I end up with m points in this box. Okay? But in fact, the object that I'm looking to identify is usually small. It's somewhere in here in small, so k is the support of the reflectivity. So at each point in the image window, I associate a number, the reflectivity of an object. It could be 0 if there's nothing there. So I have a vector of size m that I want to determine, but in fact, the support of that vector, the size of the non-zero entries in this vector, is k of them, and k is usually very, very small. So k is much, much smaller than m. Okay? And one more thing that I want to assume is that the number of sensors is usually much, much smaller than m. So this says that the system is underdetermined. In other words, the region I want to explore, yes, please.
I'm sorry to interrupt. This may lead to confusion later because m and k are interchanged from the slide.
Oh, okay.
Right, you've got.
Okay, sorry. Yeah, you're absolutely right, Charlie. So this is m, k. Yeah, m and k. Am I right now? Yeah. Okay, I think some of the slides might have it reversed, but I think now that you have been sensitized to this time revert to the symbol reversal. Okay. All right. So, but anyway, the idea is that there are relatively few sensors compared to what I want to explore in here. So the system that will emerge, the linear system, will be underdetermined. This vector of reflectivities will be very large compared to the number of measurements that I have here. That's one thing. And the other thing is that this vector is very large, but in fact it has a relatively small support. So those are the two things that are characteristic in imaging. I can change them. It's up to me. This problem is not God-given. I make this problem up so that I get something interesting out of this. Okay. Now, here's what the important quantity to look at is. It's so in the frequency domain. So nothing is moving. If the object, nothing is moving here, everything is static, I can analyze the problem one frequency at a time. So the quantity of this represents maximal information. It's a complex number. It's the Fourier transform of the signal. This signal here, Fourier transform it. Okay, for each frequency, I get if I send a unit pulse, and here it's also. And so I assume that you send an impulse from here. I will come back to the actual sending a pulse with a finite size. Then at this frequency, the impulse response when I send the impulse from XS and I receive it at XR is this matrix, P hat of omega, which in the simplest case, when there's no multiple scattering, it's very simple. It's the Green's function, the homogeneous Green's function. Kappa is the wave number, omega over C. C is the speed of the homogeneous background medium. So you go from XS to the general point Y and J, right? And then there, if assuming that this object, that this pixelization is done so that it's really a collection of pixels here. These are smaller than the wavelength. Then they send back a signal that is a spherical wave. So this is the intensity, the strength of the signal that has arrived to the scatterer. Then this is the scattering amplitude alpha j. And then this is what returns, a spherical wave that returns from the scatterer y and j to xr. And you sum from 1 to k, and this probably should have been n, no, k, it's the number of points in the image window, everything there. Okay, of course, many of the alpha j's are going to be 0. Okay, so this is the array response matrix. This represents complete information. If I have this information, I have everything I can possibly have about this this object. Now, of course, here there are two things. Keep it in mind. This will denote simultaneously the measurement that I make and also this model. So this is a model for the measurement I make. This is what I record. And I believe this is what it looks like if I knew what the alpha was and if I knew where it was 0 and where it was not 0. That would tell me exactly where the scatterers are and how strong they are. And if there was no multiple scattering, so I can have this very simple model here. Now, so the inverse problem, by the way, notice two things here. Oh, yeah, let me say this first. So if I have, of course, I don't need to have, since illuminations play a big role in what I want to say, given an array imaging configuration, all the information for imaging is contained in the full response matrix we had. I've already said that, including phases. So here I am assuming that I have all the phase information recorded. In this case, given a set of illuminations fj, now I consider for each j is an index that labels the illuminations. For a given illumination, that means it's a complex number. For each frequency, it's a complex number associated with each sensor. It is the Fourier transform of the signal that is going out, that I send. For example, it could be a Gaussian, it could be something, anything you want, that has a carrier and a base signal that could be something that is, let's say, relatively broadband, so it's narrow in time. And then, so these are the illuminations. J is from 1 to as many as illuminations as I want. This is a vector of size capital N, as many sensors as I have there. And so I multiply the response matrix by the illumination vector, and I get my data. This is the recorded data for a particular illumination vector F super J, frequency by frequency. So presumably this is what I record. Correct. I may not have the p hat, the whole p hat itself. The p hat I get by sending successively, let's say, unit vectors here. The components of the illumination vector are this, as you can see here, the n size. All right, so I have now, I can talk about the inverse problem. The inverse problem is this. It's a little bit abstract, but if you remember that I had, well, let me just go back a little bit. The inverse problem requires a model. So here's the model I'm going to use. Notice that this P, the recorded array response matrix, is a linear function of the reflectivities. Okay? So therefore, I'm going to write it. So I multiply this P with a vector F. So there's a matrix multiplication on the XS. And then I rewrite the whole thing as a linear system. So A sub F is what this product of Green's functions multiplied with the illumination F is a linear operator, it's a matrix acting on the set of reflectivities rho. Okay, and here I think I've changed the K and the M, equals B. This is what I record. This is what is being recorded. This is the model matrix, and this is the unknown reflectivity vector. This is the linear system of equations that represents the inverse problem. Measure the B, determine the rho, solve this linear system. This linear system, I'll write it over here. A F hat rho for each omega is B. This is a matrix that's of the form n by, now I'm going to mess this thing up. So, right, so, okay, let me stick with this K here. So this is n by m. This is an m by 1. And this is an n by 1 vector, okay? and the support of rho. So I'm going to erase this so that I don't contradict myself too visibly. The support of rho is K. Okay, so this is the problem. Yes, please.
Do you have the same number of sources and sensors, or?
Yes, here we do. Yes, yes. So here we do, but we don't have to. Here it is actually a square. It's a the matrix P. So the matrix P hat. This is not the matrix P hat. The matrix P hat is an n by n matrix. P hat of omega is an n by n matrix. The same number of sources and receivers. It's a transducers. And this matrix is symmetric, but it's complex symmetric. It's not self-adjoint. The symmetry is simply reciprocity in wave propagation. And that's it. It doesn't have to be Hermitian. It's not Hermitian, in fact. OK, so what is known about this matrix A, it's very simple to write in terms of these Green's functions G. It's a very elementary thing to write down. And you can form the matrix A star A and the matrix A star. It turns out, and this is really an important part of the physics of the problem, if you choose the discretization of the box here, presumably this is what it is, or you can choose it how you want it. You can choose if the numbers, the physical parameters and the pixelization are well chosen, then the product of these two matrices, this matrix A star A and A star, are nearly diagonal. Okay, that's a very important statement because it says that this problem, as an inverse problem, it is really well posed. And there are two ways in which you can, since it is underdetermined, this vector rho is much bigger than the data that I have, then there is a non-uniqueness in the problem, and the uniqueness is established by requiring that the rho is the smallest vector that solves this system. Let's say smallest in the L2 sense or smallest in the L1 sense. In either case, this is a well-posed problem provided that these matrices are reasonable. If they're close to diagonal, then I have complete control of this problem. Okay, so both L1 and L2 inversions are considered here. They have different properties. L2 is the one that is used in 99% of all the physics problems out there. This is standard migration in geophysical imaging, in radar. It's always the L2 inversion of this. I'll leave it abstract. I won't write down the formulas in detail, but they have a very simple interpretation, a very simple physical interpretation. It's called migration. The inversion of this in the L2 sense is has a history, I would say, since the 1960s or so. It's widespread. It's written in software. It's written in hardware. It's built into hardware. It's really something that is ubiquitous today. The L1 version of this, why would anybody want to do the L1? The L1 version of this is interesting because it deals with the sparsity issue. And it was found relatively recently, the last 5 to 10 years, that if you solve this problem, if you look at this problem as an L1 problem, then you can improve a little bit the resolution, provided that the vector that you're looking for, the rho vector, has small support. But this is a nice statement to make, and I've extensively myself explored this in the last few years. But there's a catch, and the catch is in this issue of coherence. So I haven't mentioned coherence yet. This is standard imaging. And now I'm going to say something about coherence because these statements change the moment you put some uncertainty into the problem. So how is coherence lost? I mean, this is a highly idealized situation. Idealized in what sense? It's idealized in that here are 3 mechanisms in which you can lose coherence. One is instrument noise, and that is that the intensity, the reflections that you get from here, by the time they arrive at your array, are very weak signals. And therefore, when they are recorded with noise. They have to be amplified, and therefore the amplification process at the array introduces noise. And so you might have very noisy measurements, low signal-to-noise ratio. Low signal-to-noise ratio is, roughly speaking, signal-to-noise ratio in which the energy of the signal compared to the energy of the noise could be comparable. That's 0 dB SNR, signal-to-noise ratio. Now, you can have that instrument noise in some sense is not so bad. If you look at the problem, if you approach the problem, I'll say that in the next slide. So that's one thing, instrument noise. And as I said, it can be bad, but it's not so bad. Inhomogeneous random medium, that's the worst, that's the real limitation of coherence. And that is that the medium between your array and the object that you're trying to image is not going to be homogeneous all the time. It's going to be inhomogeneous. You can, for example, the standard, the earliest or one of the most striking ones is when we observe the sky, when we look up into the sky, and the visual images of celestial objects that come back to us go through the atmosphere. And therefore, by the time they reach us, they are degraded. So the degradation of the optical image of an object coming through the atmosphere, the medium is not homogeneous, the atmosphere, it distorts. That's a huge problem. We lose coherence by the time the optical signals reach us down on the Earth. They have been corrupted, we have lost coherence. We go into all sorts of expensive propositions to put telescopes up on top of mountains in the desert, or to fly satellites very high up, so outside the atmosphere, to get a clear view, to restore coherence. There are no good ways to restore coherence when the medium is random, and the difference between, by the time you go away from imaging with waves and imaging with something else that goes through any homogeneous medium, like, for example, radiative transport theory. Radiative transport theory was invented as a phenomenological theory more than 100 years ago by astrophysicists so as to interpret what we see when we look up into the atmosphere, through the atmosphere into the sky, to interpret exactly the signals that we see there. And therefore, if you're going to image for signals that go through the atmosphere, you have to use, as a model-based theory, you have to use radiative transport theory. You immediately lose resolution tremendously when you do that. There are other more medical imaging applications where you lose, for example, when you use optical scans to detect anomalies in the skin or in infants through the skin to see anomalies in the tissues. These are also incoherent imaging situations because the mean-free path of a signal, of optical signals going through tissue is very short. It's of the order of, well, microns is the wavelength, is of the order, let's say, of the order of maybe, I would say 100 wavelengths would be already a lot deep into the sample. So here's the third one, instruments unable to record at high sampling rates, so intensities only are recorded, not phases. That is ubiquitous. As I mentioned, it's ubiquitous everywhere, from anything above more or less this gigahertz regime. For example, it's ubiquitous in all X-ray imaging, and certainly also in optical. And so what I wanted I have one more general slide, and then I'm going to go to the last one. I'm only going to talk about them. So this is a slide where I explain how to deal, or what we know about the loss of coherence in the, did I mention? There's one more loss of coherence, which I didn't mention. This is the last one. One other mechanism is random opportunistic illumination associated with passive radar imaging. I have spent, of all these things, I spent time in all of them, and I just finished writing a book on the last one. But I thought I didn't want to talk about this one. I want to talk about that one, because that one, this is the one that I did the most recent research, and I thought it might be, well, it hasn't been, it's kind of in progress, it's in my head more. So here, how do we deal with these things? So this is something that you probably don't know, and I think I was very surprised by this when I discovered this, first with numerical simulations, and then with a little bit of theory, but still a good theory for this doesn't exist. And it says the following: when you have low signal-to-noise ratio, okay, the main fact is that when you do the L2 inversion, when you look at this linear system, so you replace in the linear system AFB, you replace B by B plus noise, okay? This is all it is. Noise, however you want it, reasonable noise, independent and so on, over time and over frequencies. Now, if you do that and you do an L2 theory is very, very good at handling noise. The law of large numbers comes in. It's really almost as if you don't have any noise. Even when you have very, very high noise here, you get the rho with very good fidelity. There's a trade-off. The resolution goes down a little bit, but you get the rho very stable. When you go to L1, where you really get very, very sharp resolution on the rho, then an interesting thing happens for which we don't have a good theory. It says the following, that if the end, the noise, is below some threshold, then the L1 will recover with very high fidelity, with very high resolution, the rho, especially the support of the rho. But when you start increasing the noise, it goes above a threshold. There is a threshold phenomenon. It's not a sharp threshold unless the system is very large. When the system is, it's like a phase transition. Then you don't get anything. Above that threshold of noise, you get nothing. You cannot even recover the support of the rho. It just, the whole inversion process collapses. Some very interesting work in this area has been done by Dave Donahoe with other applications in mind, but this is a very interesting subject, and to find out where the threshold lies in the L1 inversion is a very difficult problem. You can only get at it quantitatively when you go to the very large matrix limit and you use judiciously ideas from random matrix theory. Okay, so this is the status of that. When you go to random media, the situation is what I was describing. This same threshold behavior, this same transition from coherent to incoherent, from wave to transport or diffusion imaging, is a very difficult one to pinpoint. So I spent many years working on the weak inhomogeneities, when the random medium is relatively weak, and you try to take away the scintillations. We look at what is the most visible effect of the inhomogeneity of the atmosphere when you look into the sky at night, is the scintillation of the stars. The scintillation of the stars is, a number of people have written about it. There's a famous paper by Chandrasekhar. Chandrasekhar was never at Princeton, or was he? I don't remember. He has a very interesting paper in 1943, stochastic problems in physics and astronomy. It used to be that this paper of Chandrasekhar, everybody knew about it. In my generation, the physicists at least knew it. I don't think anybody in this room has heard of that paper. Am I right? You've heard of it? Okay, Victor. Okay, you've heard about it. Okay, so that's a very good paper. I still recommend it. You can find it easily, Chandrasekhar, 1943, stochastic problems in physics and astronomy. And he talks about the scintillation. And a little bit later also, Chandrasekhar, with his usual very, very precise style, no nonsense, just get the facts, ma'am, nothing more. He really gets the scintillation very nicely. He really studies the Iconal equation. He assumes that you're dealing with geometrical optics. He studies the Iconal equation with a random index of refraction. And he does a small perturbation analysis, and he gets a very nice quantitative analysis of that. Now, what I did was a little bit different. Not all that different. I said, leave the wave in there, assume that the travel time, it's almost the same thing. Assume that the travel time that is going from the scatterer to you is slightly random. It's not exactly deterministic. Travel time is the distance divided by the speed. If the speed is random, if the speed in a homogeneous medium, the travel time is going to be uncertain. If there is if the travel time is slightly random, how should you image? How should you solve this system? How should you solve this system if in the system the model, you don't know what the random medium is, okay? So so here's why this problem is interesting and difficult, is when when you go to this model, with the real data, when the real data is coming out, you have here the random Green's function with a random travel time. It doesn't look like that. It doesn't have a simple formula. So this is the random Green's function that's going through the inhomogeneous medium. But when you try to image, you don't know what that is. You're going to try to image as if the medium is deterministic. That's catastrophic, because your data goes to the random medium. You're trying to image with a deterministic model like this. How are you going to deal with this? That's the fundamental problem of loss of coherence. And what we proposed when things are relatively weak is to deal with correlation functions. In other words, instead of dealing with recorded signals that are like that, when you have inhomogeneities, the recorded signal has a lot of coda in the back from the multiple scattering. What you do is take these signals, cross-correlate them, and backpropagate them. I didn't say what backpropagation really means, but you can visualize it. Backpropagate the signals, it's the L2 inversion at the level of cross-correlations, at the quadratic level. So that turns out to be reduce considerably the effect of uncertainty, but it only goes a little bit into this direction, and we don't really know where the threshold is, where wave propagation imaging becomes useless, and you have to go into transport theory or diffusion. We don't really know what that threshold is. So now I have maybe 5 minutes to say what the last thing is. So now the question is, what if you don't? So the medium is homogeneous. The only uncertainty is I cannot measure phases. It's a classic problem of loss of phase information. So what do I have? Is I say, first of all, I only measure the intensity of the B's. I don't have the B. I only have the absolute value of the B's. And I write the absolute value. Remember that, in this form, it is the array response matrix multiplied. I suppress the row in this form. So I have the array response matrix at frequency omega, the illumination F super J, and this is the absolute value of the data that have no phase information in the data for the jth illumination. Okay. Now, very simple. I go over here, and now I notice the following. This is a comment. I will skip the details of this. I will trust that you will believe me. So. If you know, of course, the array response matrix, you have the P hat. You have all possible information available to you. I claim that if you have this P star P, this M hat matrix, it's called the time reversal matrix, that's also enough. Why? Because the P hat has both phase and amplitude. Now, when you look at this M, it has amplitude squares, but it also has differences of signal, of phases. It doesn't have the absolute phases, but it has differences of phases. So it really has all the information. So it turns out that there are very good methods for imaging with this M rather than with the P. So accept that, and having the M is as good as having the P for imaging purposes. Okay, now, once you see that, then you realize the following thing, that if you look at the quadratic form of this matrix M, this matrix is actually Hermitian, because it's, well, you can see it. This matrix M is Hermitian, even though this is complex symmetric. Okay, so then you look at the quadratic form of this matrix, and you see that this quadratic form is completely determined by the intensities of the recorded signal. This is P hat, F hat, absolute value squared, this B, absolute value of B squared, this B. So it turns out, if I want to recover from the quadratic form all of the matrix M, all I have to do is use the polarization identity. Now, the polarization identity is absolutely a trivial thing, how you recover a Hermitian matrix from its quadratic form. And the only thing that is required is that you have enough Fs, enough illuminations. If you put enough illuminations in there, you can recover everything. Now, it turns out that you need of the order of n square illuminations. So the first observation is that if you have enough illuminations, there is no issue. You can recover all the phases. Okay, one way to deal with imaging with a time reversal matrix, I went too fast. maybe I should, yeah. So the real issue is now n square illumination, that's a lot. This one, for the matrix P, I need of the order of n illuminations, exactly n illuminations to get a full matrix P. N square illuminations is a lot. So the real question is, do I need them all? And it turns out that you don't need them all. You need, there are two, when I wrote this, there were two results. One thing is, what if you have only some illuminations of the order of n or a little bit more illuminations, but you're missing some illuminations, can you still determine all the elements of the matrix M? It turns out you can, and that can be formulated as a matrix completion problem, completely as a linear algebra problem. That is not a good way of doing things because it doesn't really take imaging into consideration. Another, a much more interesting, a recent result that we got says that with exactly n illuminations, not n squared, you can recover the full matrix M, provided this matrix M comes out of the imaging problem. So if you use the fact that this M is not any matrix, but is a time reversal matrix of imaging, you get all its phases. And now I have one last comment I will make, and I will stop for you to ask questions, is the following, to connect it with the Fourier transform. If you take this system here, and you move this object very far, the range is very far, and the array is relatively small, then this matrix A, the matrix, so if you have P hat, F hat equals B, okay? So this is the illumination, this is the array response matrix, and this is what you record, okay? Then when you go to this very far away range with a relatively small or small wavelength with a relatively small aperture here, then you move into the so-called Fraunhofer regime, in which the spherical waves always appear to be plane waves. And in that case, imaging is really all about Fourier transforms. This array response matrix boils down to a discrete Fourier transform. It says the following. The data on this array, the data you record here, is nothing but, you have to assume that this box is really one-dimensional. It doesn't have a range. It's really more or less on a plane. That's not a big restriction. In that case, the discrete Fourier transform of the reflectivities here is exactly what you record here up to phases. And the discrete Fourier transform of the data that you have here up to phases again is exactly the image that you get over there. Okay? So that is very simple scaling with a little bit of asymptotic analysis of that Green's function to make the phase, to linearize the phases, to make it like a Fourier transform. When you realize that, then what this is telling you, this idea of the polarization identity tells you, is that you can actually recover the reflectivity. You recover a function from the absolute value of its Fourier transform if you have enough illuminations in this language. It turns out when you move into this Fraunhofer regime, we have an array of size n with a fixed number, 8 to 16, depending on the configuration, 8 to 16 illuminations, independent of the size of the array, independent of the size of the object. You can recover exactly all the phases in the array response matrix, and therefore you have a reflectivity. You recover the reflectivity as if you have all the phases. So this is the result that I wanted to communicate. That's not important to show some results. I'll stop here and take if you have any questions. Thank you.
Questions?
Yeah?
Could you show results?
What?
The question, could you show results?
You mean numerical results?
Could you show
Pictures?
the results?
Well, okay, I'll show the results. It's basically the... So there are too many acronyms here to explain what's going on. So why don't you come and talk to me, because to explain this I need about 5 minutes to say what the various inversion methods are. I thought that, and what we have tried here is that what these figures show is that matrix completion, the linear algebra problem, requires many more illuminations to be effective. You put an imaging situation that is reasonable, and then you ask how many illuminations do you really need to get a good image, and then you use matrix completion, and you need a lot of illuminations. You don't need n squared, but you need a lot. If you realize that this is an imaging problem, and then you say, what illuminations are really good if I have array imaging? And you use only those, there are very few, and you do extremely well. What are the good illuminations? Suppose I have an array like that, okay? And I'm trying to image here. What is your intuition? How should I illuminate from here to get the best possible image here? Do you have any intuition on that? Okay, I'll tell you. You have to, the best thing to do is to image from the edges here. Because if you image from the edges, you have the best person, it's a triangulation issue. Imaging is really some modern analytical way to triangulate. Okay, you receive signals back from different places, and from the differences in the arrival times, you determine where this object is. So the further apart the sensors are, the more likely it is that you will get a better triangulation. So edge illuminations are very good, and it turns out that's what the numerical simulations show.
One more question.
So you mentioned matrix completion here, so I'm just wondering where the low rankness comes in, because it's a Helmholtz-Green's function, right? So it's not diffusive imaging.
Oh, the matrix completion is that you have this. You try to image with a matrix M, this time reversal matrix, by however you want to do it, or with a matrix P, where you're missing some of the elements. Okay. And then the matrix completion is just purely a linear algebra method. So suppose I have a matrix, a Hermitian matrix, and it has to have some properties that the columns are relatively independent, not very strongly linearly dependent, and then some elements are missing. Can you find out what these elements that are missing are?
But I mean, usually this requires the rankness of the matrix or something like that.
It requires a what?
This requires the matrix low rank.
Low rank.
Yeah, so usually this requires the matrix to be low rank, right? So I mean, I'm just wondering where this low rankness comes in here, because it's the Helmholtz sort of problem.
It's not that I've stated it differently. It's not a low rank issue. It's an issue of another terminology that's used, an issue of coherence of the vectors. You need to know, for example, if you have a matrix M where all the elements are random, then how are you going to fill in if the elements are completely random? Okay, so that issue does come in. Okay?
Michael?
So you had mentioned that there's an instability in the L1 inversion.
Yes.
Low SNR.
Yeah.
In contrast with L2 inversion.
Yes.
Is there some intuition there?
I first discovered this on my own in numerical simulations. And then I went into the literature of people who do sparse exact recovery with L1. And I noticed that there was no mention of this. And I talked to some people. I talked to Emmanuel Candes. I talked to Baraniuk, Rich Baraniuk, who's interested in this imaging thing at Rice. And he said, and the Rich Baraniuk was very frank, said to me, oh yeah, everybody knows this, but it's not written down anywhere because the subject would not look so interesting if you pointed this out. So the answer is that everybody knows this, and it's a dirty little secret. They don't talk about it. But Dave Donahoe really went head on with this, and he, as I mentioned, the intuition. I don't have a physical intuition, but my intuition is like this from the numerical simulation. My intuition is that there's something artificial about when you hear this word exact recovery, when you have very high signal-to-noise ratio, very low noise, then you get exact recovery. You get the L1 gives you back without any error exactly what rho and its support is. And this is a little bit of a fake, because the L1, what it does is, if you look at it from the computational point of view, L1 inversion and L2 inversion are similar except for one step. In L2 inversion, what you're doing is you think of the problem as a variational problem. You write solving this linear system, minimizing the L2 norm, as a minimization problem, where you successively, it's a gradient minimization problem. So you calculate, it's a gradient descent, you start from some guess, and you calculate a row through successive gradient descent. That's L2 minimization. L1 minimization is the same thing, where at every step, when you take the gradient descent, you introduce an additional step. What is it? It's a thresholding. With a vector that emerges, after you do the gradient descent, you threshold any component that it has below some value, and you repeat. So it's a denoising. The L1 is doing a denoising. And therefore, the fact that it gives you the support accurately and it has this exact recovery is through this, let's call it artificial step of thresholding, of denoising. Now, denoising is not going to work if the noise is very high, because you're going to cut off what? I mean, the things that are going to fluctuate are going to have big tails. Okay?
Let's thank George again.